We have already seen what is meant by ANOVA or analysis of variance, where we have only categorical inputs in our system. The number of categorical inputs defines the way of the ANOVA. If we have only one categorical input, we have one-way ANOVA, two categorical inputs, then two-way ANOVA. In general, we can have k-way ANOVA. The theory of all these different types of ANOVAs are remarkably similar. So, typically one discusses just one-way ANOVA and two-way ANOVA. In this lecture, we will start to take a look at one-way ANOVA. One-way ANOVA Part 1. We start with the reminders that a factor is a variable that can take one of several levels used to differentiate one group from another. A statistical experiment has one-way or completely randomized design if several levels of one factor are being studied and the individuals are randomly assigned to its level. That is, there is only one way to group the data. Example, 4 levels of nematode quantity in seedling growth experiment. Analysis of variance, ANOVA, is the technique used to determine whether more than two population means are equal. One-way ANOVA is used for completely randomized one-way design. A two-sample t-test assuming equal variance and an ANOVA comparing only two groups will give you the same p-value for a two-sided hypothesis. H naught mu1 equal to mu2, H naught mu1 equal to mu2, H a mu1 not equal to mu2, H a mu1 not equal to mu2. One-way ANOVA, t-test assuming equal variance, F statistic, T statistic, F equal to T squared and both p-values are the same. Note, but the t-test is more flexible. You may choose a one-sided alternative instead, or you may want to run a t-test assuming unequal variance if you are not sure that your populations have the same standard deviation sigma. One-way ANOVA Introduction 1. We first examine the multiple populations or multiple treatments to test for overall statistical significance as evidence of any difference among the parameters we want to compare. ANOVA F-test. If that overall test showed statistical significance, then a detailed follow-up analysis is legitimate. If we planned our experiment with specific alternative hypotheses in mind before gathering the data, we can test them using contrast. If we do not have specific alternatives, we can examine all pairwise parameter comparisons to define which parameters differ from which using multiple comparison procedures. Random sampling always produces chance variations. Any factor effect would thus show up in our data as the factor driven differences plus chance variations error. Response data equal to fit within parentheses within quotations factor or groups plus residual within parenthesized quotations error. The one-way ANOVA model analyzes situations where chance variations are normally distributed n0 sigma, so that Yij equal to mu I plus epsilon ij for I equal to 1 to k and j equal to 1 to ni. The epsilon ij are assumed to be from a normal 0 sigma distribution. The parameters of the model are the population means mu1, mu2 up to mu k and the common standard deviation sigma. The comparisons of different means from the different populations in ANOVA can be graphically represented as follows. There are a number of curves, each look like bell-shaped curve. They are centered at different points mu1, mu2, mu3, but their scatter are all equal, where the plot represents 3 probability curves symmetric about 3 different means. Considering the 3 factors from these 3 populations, we wish to compare the means mu1, mu2 and mu3. Sums of squares measure 3 sources of variation: groups, variation among group means, error, variation within groups or residual variation, and total SST equal to SSG plus SSE. Degrees of freedom for each source of variation are as follows: total sum of squares n minus 1, sum of squares due to the groups k minus 1, sum of squares due to error n minus k. We have k independent simple random samples from k populations or treatment. The ith population has a normal distribution with unknown mean mu I. All k populations have the same standard deviation sigma unknown. The ANOVA F statistic f equal to SSG by k minus 1 divided by SSE by n minus 1 tests H naught mu1 equal to mu2 equal to dot 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 equal to mu k. HA, not all the mu i's are equal. When the null hypothesis H naught is true, F has the F distribution with k minus 1 numerator and n minus 1 denominator degrees of freedom. The F test statistic that we use to perform the equality of means test in one way ANOVA is given by F equal to MSG by MSE, SSG by k minus 1, SSE by n minus 1. MSG is the mean square of each of the groups, is not same as monosodium glutamate, though it is the same abbreviation. Measures how different the individual means are from the overall mean. Weighted average of square distances of sample averages to the overall mean. SSG is the sum of squares for groups. MSG is equal to n1 into x1 bar minus x bar whole square plus dot 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 plus nk times xk bar minus x bar whole square divided by k minus 1. MAC, the mean square for error, is the pooled sample variance and estimates the common variance sigma square of the k populations. Weighted average of the variances from each of the k samples. SSE is the sum of squares for error. MAC has this complicated formula. You can easily understand that the denominator is not n minus 1 but something else. This is a little exercise for you to correct all the formulas as given. In order to perform ANOVA, we keep in mind the following assumptions. Each of the k populations must be normally distributed. We check it using the histograms or normal quantile plot. But the test is robust to normality deviations for large enough sample sizes, thanks to the central limit theorem. We wish to answer the following question: do nematodes affect plant growth? You may not know what nematodes are, but you do not need to understand that in order to do statistics. That is the beauty of statistics. We do not need to understand any setup whatsoever, we only crunch numbers. To answer this question, we fit the given data using the LM function in R and look at the ANOVA table. The R code used is as follows. You will possibly notice if you read carefully that neither the LM function nor the ANOVA table has been used. Instead, what has been used is called AOV, but the difference is insignificant here. The R code as given is greater than response less than minus C parenthesis 10.8, 9.1 etc., etc., etc. goes to the next line and is closed with one parenthesis. You must understand that the first greater than sign is called the prompt. It is not printed by you, it is printed by R. And the second less than sign is actually part of an arrow. So, it is not less than minus, it is actually an arrow, which means it is an assignment statement, that is these C 10.8, 9.1 etc. are assigned to response. Similarly, treat less than minus C rep 04, of course you understand what is meant by rep from your earlier R classes. So, I am not explaining it any further here. And nematode, as you already know, is a data frame of response and treat. So, now you find out ANOVA using AOV and you get summary of ANOVA in this way: DF, sum, SQ, mean, SQ, F, value, PR greater than F, and 3 stars. The 3 stars give you the significance scores, like 0 means 3 star, 0.001 means double star, 0.01 means single star, 0.05, 0.11. Now, the rows of the table are treat 3, 100.65, 33.55, 12.08, 0.00062. Residuals 12, 13, 3.32, 2.78. These numbers may be interpreted carefully, or you may just leave them as they are and copy and paste them in a report if you are sure that no one is going to look at the report carefully. Now, I will give you the complete One Way ANOVA Intro 1 table. This table has many columns and many rows. The first row gives you the headings. These are source of variation, sum of squares SS, DF, mean square MS, F, p-value, F clit. The second row, among or between groups, summation ni xi minus x bar whole square I minus 1 SSG by DFG, MSG by MSC, total area above a value of F for alpha. The third row, within groups or error, summation ni minus 1 Si square n minus 1, or it is actually n minus L, where L is the number of groups. So, I and lowercase l, they look both similar. SSE by DFE, blank cell, blank cell, blank cell. Fourth row, total, SST equal to SSG plus SSE, summation xij minus x bar whole square n minus 1, and followed by 4 blank cells. Notice that what was yij in the last slides have suddenly turned into xij's in this table, because this table has been taken from some other book with a different notation. In the last line, you can see R square equal to SSG by SST, which is called coefficient of determination, and square root of MSC is called SP, which is pool standard deviation. So, this is a complete ANOVA one-way table. We just now saw how to deal with linear models when we have only one categorical input. This is the simplest possible non-trivial example of linear models. Understanding its theory will help a lot towards understanding linear models in general. Even if you could not follow all the details in this module, don't worry, we are going to review some of them in the upcoming module.